Hi, welcome to Lecture 12 in the Introduction to Proof series. Here's the layout of today's presentation. We're going to, well, it looks like there's a lot of stuff, but each of these sections is brief. We're going to remind you what quantified sentences are about. This whole section is actually about quantified sentences and how to work with them better. Show some examples. Then we'll see that quantifiers can be thought of in a way that lets you use some of the rules of algebra we've just finished learning to help you with them. There's a nice little recreational math problem in the middle of our examples about this stuff, so we're going to run that. Um, the secret is to enlist some computer aid, so we'll pull up the CoCalc window and do that. And then finally, negating quantified sentences. That's kind of a big deal. I should say something, I suppose, about where we are sitting right now in the course. We're coming to the end of the section on logic, or the chapter on logic, and we had our introductory chapter that gave us a bit of the language we need. So those are really the two ingredients we need to be able to start doing proofs. And so the upcoming chapter, chapter 3, is where we actually do our first simple examples of proofs. Now, I don't count the two-column proofs we just got finished talking about as proofs per se. We mean proofs that you write in prose rather than the two-column approach. Anyway, they're coming, and they're coming quickly. And this will be fun as well as a challenge, but I'll point out one of the common skills, one of the common things you're going to need to do in writing proofs is to be able to negate quantified statements. So you might think back to the argument I showed you that square root of 2 is irrational. The negation of that was simply that square root of 2 was rational, and then we worked from there. But often the thing that we'll take the negative of is, complicated, and it often will be a big quantified statement with a lot of, maybe several quantifiers in it, and a lot of ugliness after the quantifiers, and we got to learn how to deal with those. So we'll do at least one solid example of how to do that. All right, Lo, let's get going. Consider the difference between the following. X is a prime number less than 100. There are precisely 25 prime numbers less than 100. Okay, so the first of those is ambiguous, right? It's got an X in it. And we said that before. When a sentence includes some unknown thing, a name that's not fully specified or a variable like that, you can't tell whether it's true or false. So you can't call it a statement. The second is a statement, isn't it? I went and counted. Actually, I counted twice because I was worried about messing up. There are 25 prime numbers less than 100. So a takeaway here is that you can change ambiguous things into statements by asking how many questions. If you have some thing that says X is something that satisfies a property, that's going to be ambiguous. But if you ask how many things satisfy that property, or better yet, say something like this, there's exactly 25 things that satisfy that property, you've got a statement. If the answer to how many is they all are, right? You've got a funny statement then. It's always true. It's a universally quantified thing. If the answer to how many is, well, I don't know, but at least one or some of them are, then you've got something that's existentially quantified, or something where the existential quantifier would be appropriate. The takeaway here is that quantifiers are a way to achieve non-ambiguity. Is that a bad word? To take something that's ambiguous and fix it and make it into a logical statement, something with a definite true-false value. Okay, so terminology. An open sentence, that's just a sentence that has variables in it. Here's an example. P of xy is the sentence that x is less than y. Clearly that's horrible, right? As it stands, P of xy has got two variables in it, and I can't tell you which one is bigger unless you tell me what x and y are. But add some quantifiers and bingo, you'll get a statement. So for all x in R, there exists y in R, P of xy. That's a statement. Is that a true statement? What would it say? For every number x, you can find a number y so that x is smaller than y. Well, that's just saying that for any x, you can find a y that's bigger than it. You can do that, add 1, for instance, or double it, for instance. So that's a true sentence. Here it is interpreted. For every real number x, there is a real number y that's bigger than it. Great, that's what I just said in words. Here's a slightly different quantifier thing. It says for all x in R, for all y in R, both of them are for alls, p of x, y. For every real number x, for every real number y, y is bigger than it. No, that doesn't work. So you can easily show that that's not true by finding a couple of numbers, because any number that's where x is not smaller than y is a counterexample to that universally quantified sentence. So that's a false one. How about this? There exists an x in R. That's good. There exists a y in R. They both exist. So I can find an x and I can find a y so that x is less than y. That doesn't seem hard, right? That's a particularly weak sentence. You can always show that this thing is true by naming a couple of things where x is less than y. How about x is 1 and y is 2? That'll do it. So you've just found both an x and a y. That satisfies the existential nature of these quantifiers. All right, another piece of terminology. You talk about variables being bound if they're in the scope of a quantifier. Let me back up one sec. When you see there exists x, the quantifier is that there exists, and x is in the scope of that quantifier. Here, this y is in the scope of that for all, but this y is in the scope of an existence. So they're just the variables that come after the existential or universal quantifier symbol. Okay, so when you're in the scope of a quantifier, we say you're bound. And if all the variables in a sentence are bound, you've got a statement. Sentences with some variables that remain unbound, so not in the scope of a quantifier, those are seen, and they're often seen in definitions. I think I've got an example on here. I'll move to the next page and I've got an example. So the sentence, there exists y, x is less than y, has one bound variable, y, and one unbound variable, x, right? See how y is coming after the existential quantifier, but there's no quantifier that has an x after it. Does that define a concept? There exists y such that x is smaller than y, or maybe I should say such that y is bigger than x? Yeah, actually it does. I don't know if you'll recognize that concept. That's exactly what it is. It tells you that x is finite. Because if it wasn't the case that there was a y that was bigger than x, what would that say about x? It's bigger than every other y. And so, yeah, that would be an infinite number. Here's a few more examples of this sort of thing from the book. We're going to talk about this one in a little bit greater depth in the coming section, but p of x is a sentence that just says 2 raised to the 2 to the x power plus 1 is a prime number. I think we actually already took a look at that in one of the worksheets. Q of x and y, here's a sentence with an open sentence with two variables. X is prime or y is a divisor of x. Well, everything's unbound in both of these so far. No quantifiers around. Here is something awful from calculus, but it's not that awful. L is a sentence that has f, c, and little l as variables. But if you notice, the sentence here is about the function f having a limit named L at C. And there's other junk in this sentence. It says, you see what's on the other side of the if and only if? For every positive number epsilon, so in addition to f, c, and L, we've got epsilon. And then there is a positive number delta. We've got a delta that's not listed on the argument list here. Whenever the absolute value of x minus c is less than delta, x is a new variable. It follows that f of x minus L's absolute value is less than epsilon. Written in words like that, that's fairly hard to understand, but that's the definition of what it means for the function f to have a limit L at a point C. And that limiting value, the limiting value is L, C is where it happens, F is the name of the function. These other things, though, the delta and the epsilon and the x, they're in the scope of quantifiers. You see how it says there is a positive number delta? We get an existential quantifier on delta. Where's the word that tells me epsilon is quantified to? Here it is. For every positive number epsilon. So we got for all epsilon, there is a delta such that, here's another word that indicates a quantifier status. Whenever x minus c is less than delta. That's really saying that x is arbitrary, except it satisfies that condition. Or you could think of that as part of an if-then, and then x is literally just arbitrary. Okay, so we're going to go on to look at these examples in greater depth. Here's the section 1 example. This statement, p of x is 2 to the 2 to the x plus 1 is a prime. That's the definition of what a Fermat number is. There's no quantifiers, and often when that happens, you got to notice that people are often sloppy about this sort of stuff. So there's an implicit assumption that you do have a universal quantifier. You wouldn't write that down if you just said there was some x, or there was, I'm thinking of an x in my head. If you write a sentence like that down, you're probably asserting that it's always true. Pierre de Fermat was probably asserting that. Yeah, this is the likely interpretation. For all x in the naturals, 2 to the 2 to the x, it's funny, x disappears when I highlight, but the other stuff doesn't. 2 to the 2 to the x plus 1 is a prime. Unfortunately, that's not true. I should give us a little bit of history. This guy is Pierre de Fermat. I thought it would be nice to show some of the other pictures of him. This is the one that I'm most familiar with. It shows him probably near the end of his life. He only lived to be 64. In that amount of time, well, I guess that seems like a lot of time to people in their 20s, but that's, these days people routinely live into their 80s, so it's sort of seems like a short life. Anyway, he did a lot. He was actually, they called him the Prince of Amateurs because he was not a professional mathematician. He didn't have a university post or anything, but he just loved math for its own sake. His real work was being an attorney. He would discover interesting things, and he would send off letters to famous mathematicians telling them about what they'd found. He published some papers in the journals of the day, but this was the 1600s, so there weren't a lot of them. And a lot of math actually got done sort of the way Fermat did it, by having correspondences with other mathematicians, just people sending letters back and forth. An art that's somewhat lost these days. I guess we have emails, but people tend to collaborate by getting on Zoom these days. I like Fermat. He was an interesting guy. Anyway, let me get back to the slides. Sorry, before I go off on too many tangents. It's not true that 2 to the 2 to the x plus 1 is prime, but Fermat thought it was. If you let U be the universe 0, 1, 2, 3, 4, then in that universe, this is a true thing. For all x in the U, the Fermat number is a prime number. Here's a funny thing that I just want you to notice at this moment, but we'll come back to this issue. Saying that for all x in that universe, 2 to the 2 to the x plus 1 is a prime could be rephrased as a bunch of things anded together. The sentence p of x could be replaced with p of 0. That is, this thing is true when x is 0, and it's true when x is 1, and it's true when x is 2, and 3, and 4. So that conjunction of a bunch of things really is the same meaning as the for all. Okay. Okay, well, before I go on to Euler, let us do a little sage work here. I guess I'm gonna create a new sage worksheet for us to work in. I guess the main thing I want to do at this point is simply calculate those Fermat numbers. So I'm going to do it with a loop because I'm trying to get you to think about doing programming. So my caps lock was stuck, so I had to fix that. But a loop looks like this for variable name in, and then you typically use this operator called range. Now, range is designed to give you the sort of range of values that are appropriate for the subscripts into a list or the indices into a list. Those start at zero. We always, in computers, almost always, the initial element of a list is the zeroth element. So if I want 0 through 4, I have to give it range 5. That's actually 5 numbers, right? But they're 0 through 4. In Python and in this language, that CoCalc that's derived from it, um, you specify the contents of a control block by indenting. So for I in range 5, notice how when I hit return, it just automatically indented me 4 spaces. So that's kind of a nice feature. It does mean that when you're done with the contents of the loop, you're going to want to back up, and assuming there's anything else to come after that. Well, heck, let's first just print what I is. Make sure that the loop is doing what we want. I just ran it. We've got to wait for a second while CoCalc goes out and gets a server space for us and runs this silly little program. But after that, it should go quickly because we'll be connected to a host. Okay, it does the right thing. Print I is 0, 1, 2, 3, and 4. Now I'm also going to have it print the Fermat number, which would be 2 raised to the, I have to use some parentheses to make it do the right thing. 2 to the 2 to the I plus 1. Okay, so those are the first 5 Fermat numbers. When I is 0, you get 3. When I is 5, when I is 1, you get 5. 2 to the 2 to the 1, that's 4, plus 1, 5. When I is 2, you get 2 to the 2 squared. That's 2 to the 4th, 16, and 16 plus 1 is 17. And you notice 3, 5, 17, those are all prime. You might have to do a little work to see that 257 is prime. You can certainly pull out our sheet that has the list of the primes up to 5,000 on it. And this would be tougher, 65, 537. I just want to point out that it's not beyond the reach of somebody who was doing computations back in the 1600s, though. 65, 537. Why am I taking the square root of this number? Well, because of what we learned about the Civa Veritasinis, or the way factoring works, is another way to say this. The smaller factor, if that thing does factor, will be smaller than the square root. So I'm going to take this to, I don't know, a few decimal places. 256.001. So great. We would only have to do trial division by primes smaller than 256. It's a lot, but it's not that much. I'd suspect it's about 50 or 60 primes to go through. And Fermat apparently did this work because he claimed that he knew that that was prime. Now today, in a fraction of a second, we can ask for the factors of 65, 537, and go. And it just says, well, it just says itself because that's the deal with it. It's a prime number. Fermat, on the other hand, I think they did say he computed this, but he died in like 1665. There wasn't much in the way of computational aids there. It would have been people working with pen and paper or pencil and paper trying to figure that out. And yeah, he didn't do that. So another guy, which I want to show you the biography of, Leonard Euler looked at this issue. Now, he looked at it around 1732, and he found out that 641 is a divisor of F5. So let's go back to Sage and just take this one notch farther. So there's the fifth Fermat, or the number 5 Fermat number, 429,496,7297. I can't even count. There's a comma here, a comma there. I think it's 4 billion and something. It's a pretty big number. For the 1600s, it was a real big number. Apparently in the 1700s, it wasn't quite big enough to stop anybody, or wasn't big enough to stop Euler. So, yeah, well, today we could do that in a tenth of a second, get the answer, but Euler had to do something else. I do need to say something about Euler because he's a hero. He was an amazing mathematician. Well, I think there's a bigger version of this picture. Yeah, you can see this one. If you look closely at this picture, you'll notice there is something messed up about the guy's eye. And it turns out he was blind in that eye for a short period of time. He was blind in that eye, and then it was because there was a botched surgery for cataracts. So that's a fairly common operation today. What's happening is the lens of your eye is fogging up from age, so they open up the front of your eye and take the lens out. I think they sometimes put synthetic ones in. There are some people that just don't put anything in, just have a blank there. It means you can't focus very well, but with the right glasses, you can see a little bit. Euler got that surgery done in the 1600s before the germ theory of disease was around, and so it got infected, and he lost the eye entirely. And then he began to get a cataract in the second eye, so he got a cataract surgery in that one too, and went totally blind. Yeah, so the last and strangely remained a productive mathematician after he was completely blinded. He he had a son who worked with him and could serve as his eyes to a certain extent, but he had an amazing mind. He could just hold the images, the numbers in his head and work with them. He's famous as being a calculator, somebody who could do in their head do calculations. So that's my. I've said a few things about Euler, much of which I learned from an excellent book. I shall put a link in the video description. It is called Euler, the Master of Us All, by a man named William Dunham, and it's really well written, and it presents a lot of the mathematics. It's a really good read for somebody at the place you guys are at right now. So I definitely recommend it. Okay, let's get back to work. I'll stop doing this historical sidelines. So he found that 641 was one of the divisors of F5. And this is just me being, I'm making a conjecture. I don't know if this is the case, but I think in between when when Fermat did this conjecture that the Fermat numbers were prime, and when Euler looked at it in 1732, the thing that had happened in between was a man named John Napier had created something he called the bones. They were basically they were called bones because they were often done on ivory, but they were a calculational tool. The same guy, Napier, invented logarithms, and I had mistakenly thought that since he was the logarithm guy, the bones must have been like an early version of the slide rule, but that's not the case. They were for integer arithmetic, and so I think it's conceivable, at least, that Euler set a bunch of his students to work. You work with this list of primes between 100 and 200, and you work with this list of primes between 200 and 300, and so on. They would have had the bones, so it would have been possible to make accurate computations. They could have done all that trial division using the bones, and then the kid who had the 600 to 700 thing would have been like, "Hey, I got it," you know. But there is this other thing that Euler had this reputation of being a lightning fast mental calculator. So I don't know if he had minions or if he did it himself. And I guess no one ever will know. All right, that's enough about the Fermat numbers. Although there's plenty more interesting stuff about Fermat numbers if you care to look into it. Remember the definition of a limit we had there? This is straight out of the previous slide that mentioned it. The unbound variables are f, c, and l. What function we're talking about, at what point are we taking the limit, and what is the value of the limit. X, delta, and epsilon are bound by, let's see, x is universal, delta was existential, and epsilon also universal. Let's put this whole thing into symbols now. This is a good practice to learn to symbolize everything. Oh, it goes off the screen. I didn't mean for that to happen. Well, will it? No, it's going to just continue off the screen. But I can tell you what's on the part that's going off the screen. The first thing is saying the notation we normally use for saying the limit as x goes to c of f of x is L, right? And then the stuff on the other side of the if and only if sign, that's the sentence I'm really interested in. It's the one that tells me that this limit is L. So how does it work? For all epsilon, there exists delta. For all x, and then we have an implication. Now, what's in the implication? The first thing, well, this was in the original statement, wasn't it? That x minus c in absolute value is less than delta. Here it is here. X minus c, absolute value of that is less than delta. So you can tell what's this part that's going off the edge of the screen. It's exactly what's here. The words "it follows that," or whenever blank, it follows that blank, is if and then, really, just in slight disguise. So x minus c less than delta, absolute x minus c less than delta implies absolute f of x minus L is less than epsilon. In the Jian book, there's a substantial amount of discussion about how to look at a thing like this and learn to read it. And one point that I think is a good one, which I haven't really emphasized in these slides, but you can often compartmentalize your way out of problems. The antecedent of this if-then here is that the absolute value of x minus c is less than delta. Well, what does that really mean? Having a way to describe that in sort of common language is an aid to understanding what the whole thing is. So when the difference between x and c is less than delta in absolute values, it basically means that x is kind of close to c. It's in fact within delta of being equal to c. There's a c plus delta and a c minus delta interval around c, and x is in there. That's one way to say it. So I would like to take the part that's highlighted here and introduce a phrase for you. It says x is delta close to c. Delta close is a little bit stronger than close because close has no accuracy to it. But when I say delta close, I mean within delta of c. Okay, so then let's read. Oh, and what's the other thing? Absolute f of x minus L is less than epsilon. And that's off the screen, but we can see it right here. Well, that's also the close sentence, isn't it? Except it's between different things. And it's got a different measure of closeness. This is the sentence, f of x is epsilon close to L. Okay, or the difference between f of x and L is small, less than epsilon. So that was driving me nuts that the thing was going off the side of the window. I just took a second and recompiled the slides so that I fixed the spacing a little bit. Yeah, same thing though. We were talking about this. For every epsilon, you can find a delta for every x. If x is within delta of c, then f of x will be within epsilon of L. That's the definition of the limit. We're going to come back to that thing, but yeah, for now, let's move on. So our next group of slides is about seeing quantifiers as connectors, as the same as the ands and the ors, frankly. So I already pointed this out to you in a certain place. when we have this finite universe for the Fermat problem, 0 through 4, a universally quantified sentence means the same thing as a conjunction involving all the members of the universe. So if we called that, I don't know, I think we did call it P of X before, P of N before, then we could just as well write P of 0 and P of 1 and P, like that. For all X in U, P of X just means the and of all those guys, because there's only 5 things to deal with. Now, there's a way, and it's somewhat reminiscent of sigma notation for sums. You can even denote a conjunction of infinitely many statements. Let f of n be n has factorization, has a factorization into prime power factors. Every number has such a thing, right? So the universally quantified sentence for all n in n, f of n, is an equivalent thing to the fundamental theorem of arithmetic. Or it's an immediate deduction of the fundamental theorem of arithmetic. But it means the same thing as another thing. I'm going to have to stop and fix the slides. There, that's better. For all n and n, f of n means the same thing as this symbol is a giant and sign. And that's read as the conjunction over all n in the naturals of fn. Do you see how that's similar to like an infinite sum in Calc 2? Yeah. Well, what is the upshot of that? Oh, well, before we press on, I should mention the other thing for existentials. If you have the or of a whole bunch of statements, it'll be true when any one of the statements is true. That's the very same idea as existentially quantifying something. It's true if even one of the elements of the universe makes the thing following it is true. So yeah, an existential quantified sentence is exactly the same thing as a disjunction involving all the members of your universe. There's also a big version of the or sign. That's actually right down here at the bottom of the screen. I can't highlight it because it's a double highest character. But that's a giant or. Well, here's an example, a little problem in recreational math. Find a 4-digit number that is an integer multiple of its reversal. What I mean, if the digits are A, B, C, D, I don't know if that's in the right order to you or not, but if it's A, B, C, D, then the reversal would be D, C, B, A. This is what we call an abuse of notation. Really, to say there exists A, B, C, D, I think that doesn't make sense because that would be the product of 4 variables. Really, that's what that would normally mean in algebra. But the statement of this becomes pretty painful if you have to say it, without this abuse of notation. And most people look at that and they understand, okay, he means a 4-digit number, so those are the digits of the 4-digit number. And this is an ordinary decimal 4-digit number. We haven't got any funny bases going on. So there exists a 4-digit number in Z, and there exists a K in Z where ABCD is K times DCBA. You could express that existential thing as a gigantic OR. And here it would be an OR over numbers that go from 1,000 all the way to 9,999. I guess 9,999 would work too, because its reversal would be itself, and then the K would be 1. I think we want to have there must have been a statement in the original problem that avoided the sort of trivial cases. So any number that was symmetric, that's called a palindrome. If a number looks the same forward or backwards, any palindromic number would satisfy this. So next we're going to explore that. But how many cases are there just now? Everything from 1,000 to 9,999. I think it's a lot of cases, so we're not going to do that by hand. Again, let's pull up CoCalc and see if it'll help us. Mostly I want to use CoCalc for this because I think it's good for you to see examples of coding problems. You should begin to think of a computer as a sort of an essential ally in discovering things for yourself. And let me start by mentioning that I don't want to just run a loop that goes from 1,000 to 9,999. Actually, I want to use a bunch of loops so that I end up keeping track of those digits, the A, B, C, and D. So this is what's known as nested looping, and it's as good a time as any to show you this. For A in, let's do range 10, then the control structures in Python and CoCalc all begin with a statement that ends in a colon, and then things are indented below the colon. That's automatic. What we're going to do is put 4 different loops in place. I guess let me just type for a second. So inside of that loop, there'll be yet another loop. And finally, the 4th loop inside of the 3rd loop, which is inside of the 2nd loop, which is inside of the event. Now, for now, I'm just going to try to generate the number we're talking about that has the digits A, B, C, D, and then I'll print it. All right, but this looping structure is there to make sure we're going to check that we actually go through all the numbers from from 1,000 to 9,999. So what is this number that has those digits? Well, A is in the thousands place, and B is in the hundreds place. C is in the tens place, and D is in the units place. And so let's just first print X. We'll run these loops. Uh-oh, what did I do wrong? I spelled range wrong in one of these. Oh yeah, look at that, rangy. The one thing I should point out and just own up to, the error messages in CoCalc are often pretty hard to understand. This one's not so awful, but a lot of times when error messages like this pop up, they look so cryptic, you just go, I'm not going to even look at that. If you do get one of these, scroll to the end of it and look for what's in the last sentence. That's where it usually has the part that's going to be useful to you. And it's just telling me that Ragni is undefined. Of course, I spelled wrong. That was a genuine error. I'm not just messing up for the sake of showing you this. Okay, so now, okay, great. Here's now one problem that's immediately evident is I don't want all of these. I don't want to start with the numbers that are 2-digit and 3-digit numbers. I wanted to start with the 4-digit numbers. So how could we fix that? The range operator, I feel like I may have shown you this before, but if not, let's just do this. You can get a little bit of help text on any one of the CoCalc commands that you know, or even the ones you don't know, by typing a question mark after them and then hitting Shift Enter. And this is pretty solid. It's a quick introduction to how the thing works. It explains to you that they start, well, unless you apply 2 arguments, they start at 0 and go up to n-1. Give some examples. Let's look at this one. Range ij returns I plus 1, I plus 2, up to j minus 1. It doesn't go to j. So it does start at I, but it doesn't go to j. But this is what I need for that first range operator. I want it to go from 1 to 9. So 1 comma 10 is the right thing to do there. So if I do that, I think I'll start seeing the first things are 4-digit numbers. Yeah, that's a start. All right. Let's keep going with this. How would I figure out what the reversal of a number was? Since I've got the digits inside these loops, and I hope the way these loops nesting is clear to people. What happens on the outside loop, the A loop, is that the first thing it does is set A equal to 1. And then inside the B loop, the first thing it does is set A equal to 0, or B equal to 0. The first thing the inner loop after that does is set C equal to 0. And then inside of all that, we've got 1, 0, 0, and then we see the innermost loop where D is going to change rather quickly. That's why we start all these numbers with 1, 0, 0, and then the fourth digit goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then there's one place right there where the second to the last loop, the C loop, increments once, and then another round of things for the innermost loop. So it's a little bit like the odometer in a car, right? There's one digit that's turning fairly quickly every mile. There's another digit that only turns every 10 miles. Uh, yeah, okay. So, okay, what's the other number going to look like? It is, let's just like this one, actually. Let's go ahead and copy and paste. All we got to do is change the letters, but everything else is the same. So it starts with D in the thousands place, and then it has C in the hundreds place, and it has B in the tens place, and it has A in the units place. So I don't really want to print all of these because there's like 9,000 numbers there, right? What I really would like to know is why is the reversal divided by x a whole number? That's what I'd really like to know. So how could we do that in programming? I want to only print something if that is a whole number. So we'll start with an if statement. And the condition I want is that, let's say, y divided by x is equal to the floor of y divided by x. That'll do the trick. And if it is, the stuff I want to do is print x. Let's just have that inside. That needs to be inside the if loop. Let's see if anything happens. Well, we made progress. It's not printing everything now, but it is printing a lot of things that are palindromic. And those are trivial cases. We didn't really want that. How can we prevent the palindromic ones from getting printed? Well, if it's the case that the reversal is the same as x, this number that we're looking at that is equal to 1, and then the floor of it is equal to 1. So why don't we also put in a condition? I believe the and sign works. I believe it's also the case that if you spell it out, A and D, that'll work. But let's check this first. What I want is that y over x should also be bigger than 1. Oops, I'm not wearing my glasses, but I think that looks like I got the caps lock stuck again, didn't I? Yeah. Okay, so the floor of the fraction is equal to the fraction. That means it went in evenly. And then that one bigger than 1 is going to eliminate the palindromic cases, I hope. Except I did something wrong. Yeah, it's probably that and symbol that I thought I could use. Yeah, it's not defined. Let's try just using the word A and D. The way that highlighted in the syntax thing. And now we only got 2 answers. Isn't that beautiful? One of them was actually given in the textbook, 2178. We just found, and it challenged you to go out and find the other one. I wanted to show you that it's actually not that much programming to get yourself able to find that kind of thing with the machine. Okay, so back to our slides, done with looking at that recreational math problem. Last thing we're going to look at today is negating quantified sentences. So what we're doing is really a generalized version of De Morgan's law. What I just got through saying before the whole shtick about where we went on to co-calc was that a universally quantified thing could be thought of as a conjunction, a whole conjunction of a whole bunch of things. But nevertheless, if you negate a conjunction, De Morgan's law says you get a disjunction of the negations. So a for all is a conjunction. When we negate that, we get a disjunction, and that's an exist. So the way this ends up looking is if you want to negate a universal thing, you just turn the quantifier into an existential one and put a not on the thing that comes after. And the same thing is true, well, a similar thing is true for an existential one. If you want to say it's not the case that there exists something that satisfies property P of x, it's the same thing as saying for everything, it doesn't satisfy P of x. Yeah. Watch what happens if there's bunches of quantifiers. So here's a statement that's got two quantifiers. For all in the universe, there exists in the universe, and P of xy is a statement involving the two quantified variables. But we're trying to negate that, right? We got the minus sign out front. So you bring the negative sign past the quantifier, and you turn it from a for all to exist. That's kind of very similar feeling to De Morgan's law. But now that the quantifier is in here, it's applied to something that's also a quantified sentence. It got past the for all, turned it into exist, but it hasn't gotten past here yet. We still are applying the negation to there exists y, P of xy. So do it again. Get it past the existence quantifier, and now it's a for all. And then now we're all the way to the inside, and we've got just negation of P of xy. What's the takeaway there? If you've got a bunch of quantifiers, switch every single one of them and look at the statement that comes after all the quantifiers and negate it. So we're going to see this one in action, and a sort of frightening one, but a useful one to do is the concept of the limit that we just dealt with. So the statement was, I've thrown some commas into this version of it because I think it makes it easier to read. For all epsilon positive, there exists delta positive. For all x, absolute x minus c less than delta implies absolute f of x minus L is less than epsilon. Right. Can we negate that? In other words, how do you show that the limit of f of x as x approaches c is not equal to L? I mean, that's how you'd say it in simples. Limit of x minus as x approaches c of f of x is not equal to L. Well, that should be the negation of this long quantified sentence we've got up here. So first, I'm just writing it as, all right, fine, it's the negation of this long quantified sentence that we got up here, right? Just putting the whole thing in parentheses and putting a not out front. But then let's play the game as we just saw it. That's going to be equivalent to switch every quantifier. So the for alls turn to exists, the exists turn to for alls. You'll notice, by the way, that I have left out what universe these things are quantified over. We knew that they were real numbers before, so I thought we could skip that. But it's sort of nudging at my anal retentiveness right now that we haven't said for all epsilon in R that's greater than 0. I'm going to have to learn to live with that. So anyway, the line that's currently on the screen, we've changed all the quantifiers, and then we've just thrown a not in front of the sentence that comes after. So far, so good, but we're not finished because we need to say it without the not in it. Just have to remember how to negate a conditional, which we spent a fair amount of time playing with. This is maybe the first time you've had an actual conditional with real mathematical content to it to negate. But if it's A implies B, finish your veggies, then you have ice cream. The way to negate it is to say, I finished the veggies and you didn't give me ice cream. That is A and not B. So here it is. Absolute x minus c less than delta. Same thing as saying x is delta close to c. That's A, so it goes down here directly. The other one needs to be negated. What is the negation of that piece? That is saying f of x is epsilon close to L. Well, I could say f of x is farther than epsilon from L, but the inequality, the less than sign, has a nice, reasonable way to negate it, the greater than or equal sign. So this would say something like f of x is epsilon far from L, I suppose. Right? We won't worry ourselves too much about interpreting the meaning of that, however. And with that, we've come to the end of the slides, and I think the end of the lecture as well. Um, the next section is 2.6, if I recall correctly. We'll be looking at that in the next video. Maybe a good idea to read that in advance so you'll sort of better be able to follow what I'm saying. Anyway, have a great rest of your day.